So let's begin now. Let's begin our class. So today we're going to talk about the pattern of interference for water waves, sound waves, and light waves. But I think today we will probably only have time to talk about water waves because there is a lot of drawing involved. You're going to need your module, you're going to need your pen, and you're going to need a pencil, and you're going to need a ruler for this. Okay, because you have to do this manually. You cannot just sit down and wait for me to show you everything. Like, you have to do this in your own module. So take out the pencil, take out the ruler, and also your module in order to be able to do this. Okay, so we're going to look at the pattern for light waves, for water waves, okay, for light waves, and then for sound waves. But we're going to focus on water waves first. Because when we understand how the interference of water waves works, then we can see how the rest of it works. Okay, so in the interference of water waves, okay, we have this thing called the ripple tank. Okay, and then you have two dippers over here, so two dots over here, okay, that are connected by a same motor. Okay, and so because of that, when we compare the frequency of the two sets of continuous circular waves, they're going to be equal frequency because these two dippers, dippers as if they're two small balls that you're going to dip inside the water. Okay, so the two dippers are going to dip at the same time, and so they will have equal frequency. Okay, and when you have waves that have equal frequency, okay, the name that is given to these sources, what is this called? What is the name given to sources which have the same frequency and the same phase difference? Anybody? We just did. Okay, coherent sources, very good. So these two coherent sources, and this is what it will look like. Okay, this is what it will look like if I shine a light on, if I turn on this lamp on top here. Okay, this is what it will look like. Okay, so you will see the two coherent sources, and each source is going to have a wave of its own, and the wave is going to interact. Okay, not interact, the word is superpose. The waves are going to superpose, they're going to overlap, but we call it superpose. Okay, and interference is going to happen. Okay, so this is how it looks like in a experiment setting. Okay, I'm going to play this video. Okay, sorry, let's do another one. Okay, this is another one. Take a look at the interference pattern that happens over here. Okay, you notice that there is a very blur line in between each section over here. Okay, I want you to take note of this blur line that is over here. Probably, hold on. Okay. So first of all, take note that there are these blur lines over here. Secondly, take note of these three letters. This is the letter A. This is the letter X, like from one blur line to another blur line. And this is the letter D. Okay? Take note of it first. I'm going to tell you what it means later. But I just want to show you this is the letter A. This is the letter X from one blur line to another blur line. Okay? And this is the letter D. Okay? Here's another one. Okay, this is an even better description. So let's say this is, oh, sorry. Okay. So when this one, okay, so you're going to have this interference pattern. So this is an interference pattern that happens because of the superposition of these two waves. Okay, and I've already mentioned just now that, okay, this is the letter A. Okay, just remember the letter first. Okay, then from one blur to another blur, this is the letter X. Okay, and the distance from the letter A to the letter X, okay, this whole thing, sorry, okay, is the letter D, big D lah. Okay, so I want you to get these letters in first. Don't worry about what they mean. Okay, don't worry about, oh, what is letter A, what is letter X. I just want you to know how we determine these letters. Okay, so this two is letter A. The distance between these two is letter A. The distance between one blur to the next blur is the letter X. And the distance from where you calculate the A to the X is called the letter D. Okay, in the previous video, we saw this as well. The two waves is A. From one blur to another blur is X. And then from the A to the X is the D. Okay, get that in first. All right, so the interference pattern of water is observed through this thing called a stroboscope, okay, which I cannot show you right now because we don't have one lah. I mean, I don't have one to show you, okay, but if we go back to school, I will be able to show you this. But this is an important thing. Let's mark and label on the diagram the region of constructive interference. Now, tell me, constructive interference, there are two types of constructive interference. Okay, what happens, what causes constructive interference to happen? Anybody?
Two crests and two troughs.
Okay, either two crests or two troughs when they superpose. Okay, so let's assume that all these bright lines, okay, all yang putih-putih ini bahkan, okay, we assume that all these are crests. And let's assume that all these black lines are all troughs. Okay, so we can say that because there is a very clear black, white, black, white, black, white, black, white, black, white, bahkan, so we can call this place constructive interference. Okay, where the black and the white and the black and the white, where the, remember crest and crest? This is a crest and this is another crest. When they meet together, they will form a super crest. Okay, or in the same way, if it is a trough, okay, and it meets another trough, okay, what will happen is they will form a super trough. Okay, so you assume that this black and this white, okay, are all super crests and super troughs, okay, because they already interfere. These two waves over here are already interfering. So this whole region over here, okay, this whole region, all these very clear black and white regions, everything here is constructive interference. Okay, crest and crest, trough and trough. Okay, which means that the place where it is blurred, the place where the waves are blurred out, those places, okay, are destructive interference. Because destructive interference is one crest meets with one trough, okay, and what happens? Zero. Okay, they become calm. So if let's say you put a ball over here, and I put a ball at the destructive interference place, right? This ball over here is going to move up and down a lot more. Manakala, this ball that is on the, the destructive interference is going to be kind of calm lah. Okay, I'm not going to say it's totally calm, but it's going to be kind of calm because the waves have interfered and destructed. Okay, already destroyed one another. Destroyed one another. Okay, so what happens to the water in the constructive interference region? They will move up and down with maximum amplitudes. This is really the key word for constructive interference. Maximum amplitude. Okay, super crest, super trough. Wow. Okay, and so what will happen to the water at the destructive interference region? Generally, the water will be calm. Okay, the water will be calm. Okay, so what I want you to do, if you take a look at your module, okay, if you take a look at your module at page 154, okay, page 154 over here, you will see this picture lah, kan? Okay, you will see this picture, right? Okay, so what I want you to do, let's assume that the lines that are straight, okay, let's assume that the lines that are straight, that means they are not dotted lines lah. The lines that are straight, let's assume that they are crests, okay? And then the dotted lines are troughs. Okay, do you understand what I'm saying? Okay, let's assume that the dotted lines are troughs and this one is crest. Okay, so in the figure over there, so this one is a crest. Okay, this is a crest line lah. Okay, like this crest line. Okay, and then this dotted one okay, these dotted ones, okay, are troughs. Yeah, I know it sounds like Christmas in my house, right? All these bells, cling clong, cling clong. Okay, so what I want you to do is, so you have the waves overlapping like this, right? Okay, the trough and then another trough, right? Okay, so hold on, I'm going to deal with my dogs in a little while. Okay, so what I want you to do with this one, okay, what I want you to do with this one is, I want you to circle, okay, mark a circle at all the places where constructive interference happens. That means trough meets with trough, dotted line meets with dotted line, or crest meets with crest. The straight line meets with the straight line. Mark with a circle. And then at the places where destructive interference happens, you mark with a X. Okay, destructive. That means you have a sorry, you have a crest that meets with a trough. So here you mark X. If it is a trough, if it is a crest and a crest, like this, you mark with a circle. So this one you mark with a X. Because this is crest meets trough. This is crest meets crest. Okay, if it is a trough meeting another trough, okay, then you also mark circle. As long as it is a constructive interference, you mark circle. If it is a destructive interference, you mark with an X. Okay, mark it down first in your diagram now. I'm going to give you 3 minutes to do this. Do you notice that when you draw the antinodal and nodal, right? Okay, actually it looks exactly like this. And actually it looks exactly like this, except that the antinodal region, the constructive interference region, is much bigger. Okay, it's much bigger than the nodal region. Okay, than the destructive interference region. Okay, that one is, I think, is a very important thing that we need to realize. Okay, when we draw, okay, when we draw, it looks like they are just, one single line like that. Okay, sorry, I'm going to speed through this because you already done this. Okay, so when we draw, it looks like, okay, when we draw, it looks like they are single lines like that. Right? But in reality, actually the antinodal region is very big, whereas the nodal region is very tiny. That is in reality. Okay, but the important thing here that we need to notice, okay, is this. Keep sending your stuff, everyone. Okay, doesn't matter whether I'm still talking. Doesn't mean that I talk means you can stop sending. Send it in, because that is your kehadiran for today. Okay, but the important thing is this. The antinodal and the nodal, okay, the regions where they are constructive, destructive, bahkan, okay, they are always alternating one another. Okay, alternating one another. So one region is nodal, the next one is all constructive. Then the next one is destructive. Then the next one is antinodal. Okay, notice that I am using these two words very interchangeably. Antinodal, antinode region, constructive interference. These are all the same thing, except that interference is a verb, antinodal is a region. So be very aware of that. Okay, so we've done this. Okay, to classmate all this. Okay, so I will review your work a little later, but I think everybody's one looks fine. Some a little bit better than others. Some use pen, some very brave. Okay, some very brave use pen. What if you had made a mistake? Oh dear. Okay, but I'm going to come back to remember what I said just now. I said about the 3 letters. And this is the A, this is the X, and this is the D. Okay, so in your drawing over here, what I would like you to mark, okay, is this exact same thing. Okay, you've already drawn this. So the D, okay, the D is marked from the place where you measure the A and the X. Okay, so this is the A, okay, and this is the X. Okay, from, what is this? This is antinode bahkan. Okay, from one antinode to the next antinode, or from one node to the next node. This also can be an X. Okay, as long as it is from antinode to antinode, not antinode to node. That's not X. Okay, so remember the 3 letters I showed you just now. Okay, so this is the A. A is the distance between the 2 waves. X is the distance between one antinode to another antinode or one node to another node. And then D is the distance from the wave to the place where you measure the antinode or the node regions. Okay, but in the correct terminology, okay, it will be this lah. Lambda is wavelength. Okay, A is the distance between the two coherent sources. Okay, so these are the two coherent sources. Sorry, it's Christmas once again. Okay, and then D is the distance between the two coherent sources and the point X that is measured. Okay, here. X is the distance between two consecutive antinodal or nodal lines. Means from one antinode to the next antinode or from one node to the next node. Okay, sorry, mosquito. Okay, and we get this formula, which is the interference formula, where we can calculate the wavelength, okay, by calculating the A times X divided by D. So this is a very important formula for us in this interference. Okay, lambda equals to AX over D. This is known as the interference formula. Okay, so far when we talk about reflection, we talk about refraction, and we talk about diffraction, right? There's not really much calculation, right? Interference got, okay, interference, there's a calculation that is involved, and we need to do this lah. Okay, so now what I want you to do, let's do the same thing again, but with the next gambar aja. Okay, with the next gambar aja, 155. Okay, in page 155. Now, notice that in page 155, everything is everything is crest. Okay, there is no trough over here. Maybe they're just very lazy. So let's assume that all these are crests. Okay. Now, if all these are crests, then we cannot see the nodal line lah, kan? So there are no nodes lah. Okay, so we are not going to look at the nodes. I want you to do the same thing again. Okay, circle all the antinodes. Okay, and then draw the line. Okay, and then this is where you need to do lah. Okay, you need to measure. Okay, take a ruler and measure all this. Okay, of course you're going to get this is the nodal line lah. Okay, so you find the next nodal line. Okay, and then after that you measure. This is the X. So this line you can draw higher or you can draw lower, up to you lah. But you must make sure that where you draw the X, okay, where you draw the D, where you draw this one, okay, is where you measure the X. If you put your X over here, if you put your D over here, let's say you put your line over here, then this is the X lah. Okay, so this is what I want you to do. I want you to measure. Okay, I want you to use a ruler, measure the A, measure the D, and measure this X. But you have to mark this line first in order to measure the X. Okay, measure the A, measure the D, measure the X, and then measure this wavelength. Okay, how much is this wavelength? And let's see whether we get the same answer or not. Okay, so everyone measure and then write down somewhere at the side there lah. Okay, how much is your A, how much is your X, how much is your D, and how much is your lambda. Okay, and then I'm going to call 4 people to give me their answer. Okay, 3 minutes. Okay, 3 minutes to complete this. Okay, so Alvin for A, Vivian for X and D, and then Carlson for lambda. Whoever is ready can start first.
A is 3.6.
Okay, 3.6. I'm going to assume cm lah. Okay, so A is 3.6 cm.
X is 4.7.
Okay.
And D is 8.5.
This is your D lah. Okay, everybody.
Yeah.
Thanks Vivian. So everybody, the X and the D really depends on your drawing lah, because some people may have put the D a bit higher, some people put a bit lower, doesn't matter. Okay, but Carlson, what is your lambda? How much is this?
1 cm.
1 cm. Okay, let's see whether we can prove this to be true. So the interference formula is lambda equals to AX over D. Okay, So let's put this AX over D over here and see. Let's say it's 3.6 times 4.7 over 8.5. How much will we get? I don't think we will get 1 cm though. Do we get that? 3.6 times 4.7 divided by 8.5. Oh, okay, so it's actually about 2 cm lah. Okay, it's about 2 cm. How do you get this 1 cm though? Are you sure it's 1 cm? Yeah, I shouldn't doubt Carlson, sorry. Let me just double check. Yeah, it looks like 1 cm.
Oh yeah, 2 cm.
Carlson!
Wait, it's...
Huh? Okay,
1
now
cm kan?
1 cm, hold on. Yeah, lah, actually it's 1 cm lah. Why? Why? 1 cm. Unless, but this is very unlikely lah, okay? Unless this is crest trough lah. Okay, that they forgot to. Okay, but anyway, thanks everyone for your participation. But so this is about this one lah. Okay, and then we can calculate the wavelength 3.8, 2.2, and then 8.0. So if we had used this one, okay, we would have gotten about 1.05 cm. So actually should be correct. I wonder whether the X is correct. How much was your X just now, Vivian?
4.7.
How do you get 4.7 though? From here to here.
Oh, hours. Oh,
From the first antinode to the next antinode.
oh, I think I kind of skipped the middle and then went to the left a bit.
Oh, yeah, it's okay. So remember that all these are antinodes lah, because there's no trough over here. Okay. So this is the culprit lah, 4.7. Okay, so the Carlson. Okay. No lah. Okay, Carlson is correct lah. Okay, so it's about 1.7. So it's okay. This is where we learn lah. So here is about 2 point something lah. Okay, so I hope that everybody got this. All right. So the next question is just a reminder. Okay, remember that during the superposition, sorry, this is in your module. In case you're not sure, this is in your module. Okay, so during the superposition, this is question number 2. Okay, question number 2. So remember that during the superposition, they overlap, okay, and they form a maximum amplitude. But after superposition, this one is moving on. Okay, it is going in the same direction. They don't bounce back. Okay, it's something that a lot of people always tend to forget. They think that when they meet and then they bounce back. No, waves always carry on. They just keep calm and carry on only. Okay, they don't care about overlap for what, then carry on lah. Okay, they just move on with life lah. Okay, sounds like a very sad and very dramatic teenage love story. But that's it lah. You know, you meet and then you have an enjoyable time together, and then when it's time to break up, you break up and you move on. You don't bounce back. Okay, wow, sounds so terrible. Okay, second one, A plus 2A. When they superpose, they will get 3A. Okay, and then we find that after the 2A is still moving to the left, the A is still moving to the right. They never bounce back. Okay, they always carry forward. The only way that waves can bounce, okay, is not by meeting another wave. Okay, it is by reflecting back. And how does it reflect back? It has to hit a wall. Okay, it has to hit a wall, then it will bounce back. Okay, so quite interesting. There can be a lot of very interesting life analogies here. Sometimes it is the circumstances around us that need to change in order for us to change. And it is not always because of the people that we meet. Wow. Okay, yeah. Anyway, yeah. So if waves can change direction because they encounter an obstacle, okay, it just goes to show that actually sometimes it is sometimes the circumstances need to change and not the people, okay, in order for us to change. Anyway, moral story lah. So this is obviously destructive interference, okay, because it's a crest and a trough that is meeting. So during is going to be 0, okay. What do you think happens after? Do you think they will totally disappear once they cancel each other out? Or will they carry on? What do you think? Anybody? It's very interesting.
Carry on.
Okay, they will carry on. Okay, so even if two people, wow, people again, even if two people are fighting, when they fight, right? Once they decide to move on, they just move on. Okay, there's no point holding on to something that is not worth holding on to. Wow, life lessons, betul. Okay, anyway, the point of this exercise is to show you that after superposition, the waves carry on. Okay, they don't stay superposed. Okay, they don't stay superposed, neither do they bounce back. Okay, they always carry on. Okay, likewise, all of us also. Okay, turn to the next page in your module. Okay, and this is activity 3. And this is kind of the work that I want you to do today to prepare for Friday's class. Okay, so what I want you to do for activity 3 is I'm going to, hold on. Okay, I'm going to, no, not share window. Okay, what I would like you to do, I will share this link with you. Remember our very favorite, sort of favorite lah. Okay, the interference simulation that we did that day. Okay, so what we want to do for Friday what we want to do is we want to discuss the factors that affect interference. Okay, that's activity 3. Okay, open your module to activity 3 is factors that affect interference. We have learned that the formula is lambda equals to AX over D. Okay, so we want to know what are the factors that affect interference. So what you need to do is you open this simulation, okay, instead of doing slits, do interference lah. Okay, so you click on interference. Now these are drops of water. Wow. Okay, these are drops of water where you can adjust the separation lah. Okay, you can adjust small separation, big separation. Okay, and if you want to turn the water on, doesn't matter whether you turn it on fast or slow, they will always end up at the same time because this simulation is made in such a way that it will be automatically coherent. Okay, now I would suggest that you keep the amplitude to maximum because if it is a minimum amplitude, it becomes very blurred like this, a little bit difficult to see lah. Okay, so keep the maximum amplitude. Okay, you will have to change the frequency. Okay, you will have to change the frequency when the question asks you to change the frequency. Now, remember this again, and I've mentioned this when we were talking about diffraction. Okay, frequency and wavelength are opposite to one another. If you want to change the wavelength, you change the frequency, but in opposition. So bigger wavelength, I'm going to type this in so that everybody is aware. Bigger wavelength, okay, is smaller frequency. Okay, if you want to change to a bigger wavelength, you create a smaller frequency. Okay, so you get the wavelength a lot bigger. And if you want a smaller wavelength, you increase the frequency. Okay, you increase the frequency, then you find that the wavelength becomes much smaller already. Okay. So use this simulation, okay, use this simulation to answer all the questions, okay, in activity 3. And on Friday, okay, we will discuss this activity and your findings. Okay, so you compare the distance, state the relationship. Okay, so so the graph, okay, the graph of X against A in page 156, number 5, Roman 5, Roman V. The graph of X against A, and then Roman 6, question number 4, graph of X against lambda, and Roman 3, question number 5, graph of X against lambda. All this, I think, are in your textbook. Okay, you can refer to your textbook to help you with this, but what I would like you to do to prepare for Friday's class are very important. Come to class prepared, please, so that we don't waste time waiting for one another. Okay, is answer everything in activity 3 and use this simulation to help you to see, okay, what happens when you change the A, okay, when you change the separation, okay, this is the A, right? Okay, what happens when you change the separation? What happens when you change the wavelength? Okay, and what happens when you change the D? Okay, the last one, number 5. Okay, the number 5. I think the number 5 also you can answer. Okay, it's just that maybe your D over here is a little bit different. Okay, so you can use this also to measure if you want to know like how to use this. Okay, so you just put it over here, then you mark it across here. Okay, so this A is about 4.6 lah. Okay, over here is 4.5. Okay, if you want to measure the X, remember the X is from one destructive to another destructive, right? Okay, so it's about here. Yeah, so it's also about 4.6. If you want to measure the wavelength, okay, bring this down here. I'm having fun with this all on my own, but never mind. Okay, if you want to measure the wavelength, it's best to pause so that it's easier to see. Okay, so let's say from the bright to the bright lah. Okay, from this bright to the next bright. Okay, so it's about 2.2 cm. Okay, agak-agak lah. Okay, you can use all this to help you to measure, to see how the factors, what factors affect the interference of waves. And then we will discuss this on Friday.